All right, so today we're going to talk a little bit about the third type of bonding, which is called metallic bonds. So far, we've covered ionic bonds, so that's generally between a nonmetal and a metal. Covalent bonds, which is generally between two nonmetals. Remember, with ionic bonds, it's a give and take situation with your electrons. One gives up electron or electrons, the other one accepts or takes those electrons. And usually that is a result of their very different electronegativities. The nonmetal with the high electronegativity, the high want for electrons, and the metal with the low electronegativity or the willingness to give up electrons because they're not very attracted to their electrons. So today we're going to talk about metallic bonds, and we'll come back to this picture of the ocean in a little bit, but just keep that in the back of your head as we work through this. Okay. So what types of elements form metallic bonds? This should be pretty self-explanatory. The answer is metals, right? So metals will form metallic bonds. That's really the only other option we have because we've already kind of taken care of all of the other combinations. So generally when we talk about metallic bonds, they're formed between metal atoms of the same kind. It's not that you can't put more than one metal together. It's just not considered a bond, and we'll talk about that in a little bit. So, for example, copper, silver, platinum, those are just, if I have copper, I don't just have one copper atom, I have multiple copper atoms that are bonded to other copper atoms. If I have silver or Ag, I don't just have one atom of silver, I have multiple atoms of silver that are bonded together with a metallic bond. If I have platinum, same thing. Notice the lack of subscripts in a metallic bond formula unit, so very similar to ionic substances. We give their chemical formulas and formula units, which is the lowest possible ratio of atoms in a bond. So if we're talking about copper, well, then the lowest possible ratio is a 1 ratio because that means it's all copper, silver, platinum, etc. So they don't have anything weird about their names. If I say copper, it's just Cu. It doesn't have any subscripts or anything. If I say silver, it's just Ag. It doesn't have any subscripts or anything. Okay, sort of like if I give you salt, you would know that it's NaCl. But you would also know in the back of your head that it's probably not just one sodium and one chlorine. It's probably, say, hundreds of sodiums and hundreds of chlorines in a 1-to-1 ratio. So let's talk electronegativity. So thinking about metals and the fact that we're talking about atoms of the same kind, the change in electronegativity from atom to atom would be 0 because they're the same element being bonded together. Okay. And this is different than ionic substances because if you think about ionic substances, the difference in electronegativity of the elements involved would be large because, again, metals have a low electronegativity, nonmetals have a high, so the difference between the high and the low is a large difference in electronegativity. And in metallic bonds, we're basically saying the change in electronegativity from element or atom to atom is 0 because we're talking about atoms of the same kind. And in addition to that, some of you might be thinking, well, like if I have, say, hydrogen and hydrogen, because hydrogen's diatomic, if I have two hydrogens that are bonded together, their change in electronegativity is also 0, but that doesn't make it a metallic bond. True, because not only do they have a change in electronegativity of 0, the value for the electronegativity is going to be low. Metals don't attract electrons. They tend to give up electrons because they have a lower Coulombic attraction for the electrons. And so this is what makes it different than covalent, because even though some covalent bonds have a 0 difference in electronegativity from atom to atom, covalent substances or atoms that are involved in covalent substances would have high electronegativity values. So while the difference between the two values might be 0 or pretty close to 0, the values that you're actually dealing with are high on the scale. So think about fluorine. Fluorine's a diatomic element. Its electronegativity is 4. So if I have F2, sure, the change in electronegativity is 0, but it's not metallic because that's a high electronegativity value of 4 in that element. If I'm talking about metals, my electronegativity values tend to be like 1, maybe even lower than 1. So sure, my change in electronegativity is going to be 0 because I have the same element, but not only that, the value of the electronegativity is a very low value. And so that's what makes them different than ionic and covalent substances. So in metallic bonds, it's a little bit weird and it's a little bit different than what we've seen previously. It's called the electron C model. So basically what happens is you get all these atoms together and all of their valence electrons just kind of start to float around the nuclei and non-valence shells. And that's called your sea of electrons. So as you can see in this screenshot here, all of these would be valence electrons that originally kind of like belonged to one of these atoms, okay? And so what you see happening is these valence electrons, they're now basically attracted to all of these different cations that are left behind. What we essentially do is we give up all these electrons and they just kind of like arbitrarily float around being attracted to all these cations. So in that way, it's kind of like sharing electrons, so similar to a covalent bond, but they're not just shared between, like, say, this atom and this atom. In a covalent bond, it's very clear, like, the electrons are shared from this hydrogen to this oxygen, or from this oxygen to this sulfur, or whatever. In a metallic bond, it's like, well, this electron here could be from here, could be from here, could be from here. We're not really sure. It's just shared amongst all of everybody, okay? So it's not really a one-to-one sharing ratio like we see in covalent bonds. And so the sea of electrons will surround the positive cations, because what you end up left here is basically a positive ion. You have a nucleus with 13 electrons in this case, or 13 protons, I'm sorry, and then you have 2 shells around it with only 10 electrons. So essentially these are all just like cations. They're cations with a positive 3 charge. And so as these cations have a positive 3 charge, all of these electrons that are just kind of like arbitrarily floating around in this sea, they're attracted to all of these cations that left behind. So they just kind of like bounce around, kind of like a pinball machine. They just kind of bounce around all these cations. They don't really want to leave. But if you give them someplace else to go, sure, they'll leave. If you give them a reason, that's kind of what happens. So it forms a lattice similar to ionics, but it's looks a little bit different than ionics, because this is like random electron motion that causes the lattice structure, not a give and take situation like we saw in ionic substances. Ionic substances are a lot more organized in terms of like, I'll give up an electron, you will take that electron, and we'll stick together. Metallic is not as organized. It's kind of like, I'll give up all my electrons and they'll just kind of float around here. You'll give up your electrons and you'll just kind of float around. So metallic bonds do form a lattice as well. It's just not as organized as the lattice of an ionic substance, okay? So we call these electrons in the sea of electrons, we call them delocalized electrons, because they kind of don't have a home. They don't necessarily belong to any particular atom. They just kind of like float around aimlessly, bouncing from cation to cation, and they just move freely from, within the solid. So if I take the metal cations, or the metal, like the center that's left behind, and the delocalized electrons, I can see that there's some Coulombic attraction there. So again, remember, Coulombic attraction is the force of attraction that exists between charges, okay? And we can look at that formula like charge 1 times charge 2 divided by distance or whatever. But the fact of the matter is we still have charges, electrons, being attracted to cations, and we still have an attraction there. So those electrons don't just want to like fly away. They still are attracted. It's just not as organized. So it's a little bit different than in ionic substances. So the ionic substances is when we talk about the Coulombic attraction, we're talking about the attraction of one ion to another ion. We're talking about the attraction of one positive ion to a negative ion. And ions contain protons, neutrons, and electrons. In metallic bonds, when we talk about Coulombic attraction, we're talking about the attraction of electrons to a cation. So we're just talking about a subatomic particle of electrons being attracted to a cation or a positive ion that's left behind. So it's a little bit different, but the idea is still the same, the attraction between something positive and something negative. So things that are true of metallic bonds. Number 1, they are the substance that are good conductors as solids. So remember, in order for things to conduct, you have to have mobile charges. Well, in this case, we have a lot of mobile charges because the electrons are freely moving in that sea of electrons. Those delocalized electrons are just bouncing from cation to cation to cation, and that's what makes them really great conductors. But not all metals are created equal. Some of them are better conductors. So you can see down here, we've got aluminum, copper, and silver, okay? You see their common ion charge, and you see they have different resistance values. So aluminum has a very high resistance value, whereas silver has a very low resistance value. You'll also notice silver tends to give up only 1 electron, aluminum tends to give up 3 electrons, okay? So we know that aluminum is the worst conductor of the 3, silver is the best conductor of the 3. So it seems like the more electrons you give up, like aluminum gives up 3, the worse a conductor you are. And that seems weird because you're like, well, if you give up more electrons, then aren't there more charges floating around in the sea of electrons? True, but if you give up more charges, that also means that there's a greater Coulombic attraction. There's a greater reason for those electrons to kind of not go as far as when you give up less. So if there's more electrons in the sea of electrons, they're going to tend to stay closer to the cations. If there's less electrons, then there's not as much difference in charge. There's not as much conductivity, or not as much Coulombic attraction, so more conductivity. So again, the more electrons a metal gives up, the worse a conductor it is. And that's because the more electrons it gives up, there's a higher charge, so those electrons are more attracted to the cations. All right, metals tend to be shiny. We say that they have luster. And don't need to know much about this, but it has to do with the electrons being able to absorb light and jump energy levels because they're very mobile electrons, and it's easy for you to do that, and that's what gives them their luster. So again, you can see sodium, this is pure sodium. It's very metallic. It's shiny. This is sulfur. Sulfur is not a metal. It's a solid, but it's not a metal. It looks really soft, and it's not shiny at all. Okay. Moderately high melting and boiling points. This isn't the best property. There's a lot of ionic substances that actually have higher melting and boiling points due to the lattice energy. These are kind of like in the middle. Because the lattice energy usually in metallic bonds is not as high as ionic bonding lattice energy, but it could be high. So it really depends on the metal. And the moderately high melting boiling points, just like in ionic substances, is related to the attraction of the cations and delocalized electrons. In this case, in ionic substances, it was related to the attraction between the cation and the anion itself. And that's what that lattice energy was measuring. So in this case, moderately high, because we're still talking about an attraction between charges, it's just delocalized electrons are really small. And so even though the charge is really important, the attraction might not be as strong, okay? And again, not a great property because it does vary really widely in metallic bonds. The last thing that we know about metallic bonds, they are malleable, ductile, and durable, all right? They are malleable because they are able to be shaped. You can ding them, you can bend them without breaking. And that's because the delocalized electrons can just move with the cations as you hit it. So you see this picture on the bottom right here? It's being hit and it gets dented because the cations and the electrons can move together. That's different than an ionic bond because in an ionic bond, when we hit it, we shifted the ions. They weren't moving together, and that caused the breaking, okay? They're ductile for the same reason. They're able to be formed into wires and stretched, and again, same reason, because the cations can move along with the delocalized electrons. So we're just going to stretch them out and make them take a different shape, all right? So anytime you apply a force to a metallic bond, the cations and the delocalized electrons can just move together, and that results in them being dentable, stretchable, etc. And so that's different than substances we looked at before. That's where I'm going to stop this video. There'll be one more short one about metals that are not pure.